So Jackie's a senior scientist at Sandia National Laboratories in California, working in the combustion research facility there, and a former colleague of mine, so I'm especially pleased that she can join us today. Jackie's a world-leading expert in turbulent combustion simulation. She's pioneered direct numerical simulation of turbulent reacting flows with complex chemistry, and this has led over the past decades to enormous improvements in our understanding and physical insight into these problems. She's also been very deeply involved in high-performance computing and has been a leader in the co-design of simulations with petascale and exascale computational hardware and systems. And as a result of all this work, Jackie has received a number of honors, too many to mention all of them, but I'll just mention just a few. She's a member of the National Academy of Engineering. She's won an Achievement Award from the Society of Women Engineers, the Bernard Lewis Gold Medal of the Combustion Institute, and she's a fellow of the Combustion Institute and the American Physical Society. So we're really glad that she could spend the next hour with us today and tell us about some work in turbulent combustion at the exascale. So please take it away, Jackie.
Okay, thank you, Yusuf. And thank you for inviting me to come give a talk here. I'm delighted, and I'm also a parent of a student who's attending MIT right now in undergrad. So this is exciting for me. So as Yusuf said, I'd like to talk about some of our DNS activities at Sandia Labs in trying to glean insights into turbulence chemistry interactions that occur in combustion. And we've been on this holy grail to chase high performance computing for now almost over 2.5 decades, starting from terascale computing and now approaching exascale computing, 10 to the 18 floating point operations per second, which is due to arrive within DOE in the next year or two. So combustion will continue to be the dominant source of energy for ground transportation, for power generation, and for propulsion for several decades to come. And despite the expected growth in electric vehicle sales, both due to plug-in hybrids as well as battery electric vehicles, the global light-duty fleet, the passenger cars, will still be dominated by vehicles with internal combustion engines in the coming decades. And so there's a real need to improve the internal combustion engine efficiency as an important path to energy security and also to minimize and mitigate greenhouse gas emissions responsibly. So within this charge, the Department of Energy's Vehicle Technologies Office has formed a partnership of advanced combustion engines called PACE, which focuses resources across 6 national labs listed down below on the right to try to overcome some of the common key barriers to engine efficiency. And as part of this charter, we're leveraging DOE investments in high performance computing, especially those through the Exascale computing project, and also recent advances in machine learning and AI, data-driven model development coupled with high performance computing. And we believe that in developing predictive models in this manner, that this would lead to a direct path to enabling industry OEM CFD workflows. So DNS, direct numerical simulation, is a fundamental tool where all of the fluid mechanical scales up from the largest energy containing scales down to the Kolmogorov scale are fully resolved numerically using very high accurate methods. And then we couple this with reactive flow. And so it's a tool for understanding the micro scale turbulence mixing interactions that occur in combustion that are oftentimes very difficult to measure. The diagnostics and the environments are extreme, and so it makes it very hard to actually measure these small scale interactions. But because combustion, you don't burn things until they're molecularly mixed and react, those kinds of physics can have a very strong bearing on macroscopic quantities like the heat release rate or the fuel consumption rate, which may not be resolved in a typical engineering CFD, a Reynolds average Navier-Stokes solver, or in a large eddy simulation, where those small scale interactions are relegated to the subfilter models. So there's still some challenges outstanding in trying to understand mixed mode combustion. That is where you might have flames burning into a reactive or autoignited mixture. And so problems like autoignition, and in an IC engine, you traverse a very broad range of temperatures and pressures. And so you can encompass both low temperature, intermediate temperature, and high temperature autoignition at the same time that you have premixed or partially premixed flames, cool flames or high temperature flames propagating into this reactive soup. Current models don't handle this sort of mixed mode combustion. And so there are a number of technological questions, as shown in this picture, of how we can understand how to stabilize a diesel jet flame in this low temperature combustion regime where you burn with more EGR dilution to avoid the production of soot. And in gasoline engines that are spark ignited, where there's a move to dilute heavily also with EGR, lean and dilute operation to minimize NO formation. Likewise, in the propulsion arena, there are challenges with how to anchor high-speed flow in a scramjet, for example. What kind of bluff bodies or cavities are needed to help anchor the flame. And then in gas turbines for power generation, there's a move to go to staged or sequential combustors, where the second stage would introduce hydrogen-enriched fuels that could be a byproduct of some of the renewable energy, that wind and solar that we're using, that are augmenting natural gas. And so there, in the sequential staged burner, there's also autoignition, thought to be the predominant mode of combustion in the second stage. And there are questions about how that autoignition is stabilized and whether there are thermoacoustic effects that are a consequence of that autoignition mode of propagation. From a fundamental point of view, there's still a dearth of insights into the multiphysics, things like spray coupled with turbulence or soot and thermal radiation in these highly turbulent flames that are needed to formulate physics-based LES models. In practical engines, these flows are at very high Reynolds numbers with large fluctuations sometimes in both pressure and turbulent fluctuations. They're often present with complex flows, not just isentropic turbulence, but within the presence of mean shear or flow recirculation. And by and large, many of the LES closures that we use today are inherited from our knowledge of non-reacting flows. And so there's questions still about multi-scale energy transfer processes, dilatation and gas expansion that's generated at the small scales. Where do they move in the energy spectrum? And very, very complicated time histories through these thermochemical trajectories through flames and ignition fronts. And so my effort has been to focus on high fidelity simulations, in particular DNS, as well as getting involved in hybrid DNS and LES methodologies. And we're doing this in a way that we can resolve the chemical fidelity sufficiently to be able to differentiate subtle effects in differences in fuels where there are very strong turbulence chemistry interactions. Over the years, we've started to move from DNS in a box, the size of a tofu cubed, now to more complex flows involving staged combustors and also more geometry and also multi-physics with sprays and soot. The code that I've developed at Sandia over the years is called S3D. It's a compressible reactive Navier-Stokes solver, solving for the total energy and species continuity equations. Recently, we've included multiple temperatures, accounting for vibrational non-equilibrium in addition to just thermal equilibrium. We use higher order finite difference methods. We're 8th order in space, center difference, and 4th order in time using a 6-stage explicit RK method. We can treat detailed reaction kinetics and molecular transport models, and we recently coupled it with a Lagrangian particle tracking method that allows us to use particles as tracer particles, but also two-way coupled spray, dilute spray drops, and put in various closure models for drag, heat transfer, and also impingement of sprays onto walls and splash. And lastly, we've added a soot modeling capability using the method of moments. In addition to solving the large system of partial differential equations, we also are able to solve in situ analytics and visualization. And now we're adding reduced order modeling using principal component transport and other machine learning and AI methods while the DNS is running. This code has been refactored a number of times by computer scientists for multi-threaded mini-core heterogeneous architectures, including GPUs that will appear on the DOE Exascale machines, Frontier and Aurora. So GPUs and also FPGAs and ARM types of hardware. Over the years, so I've been in this business now for about 2.5 decades, and over the years, the computational intensity of DNS has been able to keep up with Moore's law by and large. And so we've grown our DNS problem sizes as denoted by the number of grid points and multiplied by the number of variables that we transport has grown exponentially, as you can see on this semi-log plot. And the number of grid points here is indicative of the Reynolds number, which scales as number of grid points to the 9th force power. And the number of variables is dominated by the number of species and temperature that we have to transport. To describe a practical fuel of interest, such as gasoline or a surrogate of gasoline, such as isooctane, can require hundreds, if not thousands, of species. And so a big part of our job is to identify reduced mechanisms that capture the accuracy in the regime in which we want to use it. And so back in the early 1990s, we were only able to perform 2D DNS with somewhat complex chemistry, but really had no turbulence, you had no vortex stretching. And then as time progressed, we started to include 3D calculations with about 3.5 times 10 to the 9 mesh points, but with very simple hydrogen or methane chemistry. And then today, we're at the point now where we can actually simulate directly a smallish laboratory scale turbulent flame and do one-to-one comparisons in terms of the statistics sampled at different axial positions or however you want to analyze the data. And so this is a real accomplishment because we can now directly couple with experiments, and computation can inform one another of either new experiments to perform or new ways to analyze the data to extract information for model development. Within the DOE, since about 2011, there's been a huge push to develop application codes, I think 22 or 23 application codes, along with a capable software stack with a new hardware that is that minimizes power use, power footprint. And so in that exascale computing project, one of the applications is combustion. And I lead a project called PELI, which is, these are reactive flow PDE solvers using block structured AMR with multi-physics, as I said, sprays, particles with soot and thermal radiation and boundary capability in this code. And our objective is to get scalable performance portability on the exascale machines that will be deployed in the next few years. So with these, and I should say this suite has two codes. One is a low Mach code where the acoustic waves are filtered out, and you can take time steps on the order of advection. And the second code is a compressible formulation capable of handling shocks and acoustic detonation types of phenomenon. Both are coupled with the multi-physics modules for chemistry and thermodynamics. Some of the key questions that we want to address with this exascale Peli code would be to understand the distribution of reactivity in a realistic mixture of fuel injection prepared by in a diesel jet, and then a subsequent main injection that injects additional fuel that mixes with the have a big impact on combustion phasing and ignition delays. And so some of the questions we want to address are: how are the reactivity gradients affected by the composition and mixing characteristics, the duration of a given injection and the dwell time between injections, how many injections, which fuels, which component, are these fuels multi-component? And then how does the reactivity distribution and re-entrainment affect downstream emissions generations for soot or thermal pyrolysis? What are the rate controlling reactions? Can we identify those that could help expand the operating map for these efficient operation of these compression ignition engine combustion regimes? As part of this Peli project, we are working closely with the chemical kinetics group at Argonne, coupled with Bill Green at MIT, and with Chin-Feng Liu at University of Chemistry, that's based on ab initio theoretical calculations, and is tested using uncertainty quantification methods that would then be able to be reduced and produce drop-in mechanisms for our DNS. Previous to this, it would take years to develop a detailed chemical model, and then you'd have to pass it off to someone else to reduce it. And so by the time you could actually see these reduced models in our CFD calculations, it would be a very lengthy time. So we've shortened this enormously by developing this kinetics framework within this ECP project. Now I'd like to just present a couple of vignettes showing the capability of DNS on current petascale produced on Summit at Oak Ridge National Laboratory. These are IBM and NVIDIA GPUs. I think there are 6, and I think there are about 4,000 nodes, a little bit over that on Summit. And so the first example has to do with multi-injection diesel jets and modeling implications. And the second example has to do with sequential staged reheat combustion in gas turbines for power generation. And then I'll switch gears and talk about some of the computer science issues associated with how do you program these exascale machines. Are the current distributed programming models that we use with MPI and OpenMP sufficient, or do we need to look at a little bit, some other programming models? I'd like to also touch upon in situ analytics and a little bit about machine learning before I close. So the first vignette has to deal with autoignition under diesel-like conditions. And this is, we start with a simpler temporally evolving planar jet, and then using S3D, and then we will move to a spatially evolving impulsive jet so that we could deal with multiple injections using the new code Peli LM. This is work that was done by my former postdocs, Julia Borghese, Alex Chrisman, and in collaboration with Chin-Feng Liu. As we were motivated by this problem because diesel combustion involves both multi-stage ignition as well as mixed mode combustion, as I pointed out earlier, under these low temperature combustion conditions. And there's a push, of course, to try to increase the fuel efficiency and reduce emissions, especially for heavy duty engines, for trucks, and for marine engines. And we know that ignition is extremely sensitive to the fuel chemistry and especially to the low temperature reaction branch. And so the question I want to answer is, how does molecular and turbulent transport and mixing in and low temperature, coupled with low temperature chemistry, affect ignition under these diesel types of environments. And so you have nominally a cold liquid fuel being injected into a heated ambient that's at a temperature high enough to promote low temperature autoignition. And as the mixing of this cold fuel into entrained hot air mixes, you end up with large amounts of thermal as well as composition stratification that modulates how local fluid parcels ignite. This picture on the right shows the temperature plotted versus the mixture fraction and its evolution in time for diesel autoignition problems. And so you can see that initially you have this mixing line, and then you start to see low temperature ignition processes happen near the minimum ignition delay time, which I'll describe in a minute. And then it propagates into richer mixtures where the delay time is shorter. And then eventually you get the first high temperature ignition by time where this yellow line is, where the temperature peaks on the very fuel rich side, and then it propagates back to stoichiometric conditions right around here, about 0.06. And so that's kind of the evolution. So what we set up here, as I said, was a temporal slot jet where we have a partially premixed fuel slab at a mixture fraction of 0.3. This is a mixture fraction selected at a virtual origin downstream of where the liquid fuel has evaporated, because we're looking at a pre-vaporized mixture, a rich mixture at 450 Kelvin, and on either side of the fuel slab are the oxidant, which is reduced air with 15% oxygen, 85% nitrogen at a heated temperature of 960 Kelvin. We ran this calculation at 25 bar. We wanted to be at 60 bar, which is where engines experiments were actually conducted, but the resolution requirements were prohibitive. We used a 35 species non-stiff reduced mechanism. The fuel jet was 21 meters a second. This gave us a jet Reynolds number of 7,000, a turbulent Reynolds number of just under 1,000. And this was run with a code S3D Legion. I'll talk about that later in my talk. And required 60 million CPU hours running on Titan and also on Summit. To resolve at these high pressures, the ignition front structure and the premixed flame structure required 3 micron spatial grid resolution. And so our domain size is pretty small. It's about 3.6 millimeters by 1.4 millimeters by 3 millimeters, and it cost 3 billion grid cells. We were able to simulate about a millisecond of physical time, taking small time steps, 4 nanosecond time steps, to observe ignition and propagation of these burning flames throughout the domain. And so this is a rendering of a volume rendering of one of the intermediate low temperature species, hydrogen peroxide, 0.17 milliseconds after the start of reactions. This is occurring during the low temperature ignition part of the problem. For those of you that aren't familiar with autoignition, this is a homogeneous 0D reactor, and it plots on a semi-log plot the ignition delay versus the mixture fraction. And it's been known and brought forth by Nandis Masterakos that there's this so-called minimum ignition delay mixture fraction, a point of mixture fraction for which you get the minimum ignition delay, both for low temperature ignition as well as for high temperature ignition. This is low temperature ignition is denoted ignition delay versus mixture fraction is plotted with the red dashed line, whereas the black solid line denotes high temperature ignition. And so you can see the delay time is the shortest at about 0.06, just slightly rich of the stoichiometric mixture fraction, and occurs at 0.12, almost twice the mixture fraction of the low temperature ignition for high temperature ignition. And we can also see that there's, on the rich side, there's not a whole lot of separation in time between the low and the high temperature ignition. Now, one other interesting feature that we can learn from these 0D reactors is that the low temperature ignition occurs much sooner than the first high temperature ignition would occur, almost by a factor of 3 to 4 times. And hence you would expect that most of the low temperature ignition will have been completed in the turbulent jet before commencing high temperature ignition. And so in this n-dodecane surrogate for diesel fuel, the chemical mechanism is such that you have low temperature ignition, which is characterized by hydrogen abstraction reactions, successive oxygen addition, internal isomerization reactions. And these reactions with keto hydroperoxide end up producing OH radicals through chemical chain branching. It also raises the temperature, maybe about 100 to 200 degrees Kelvin. And then the heat release, a tiny bit of heat is released as shown in this plot on the top in time. And then what you see is the heat release goes down, but you start to build up and accumulate hydrogen peroxide while the temperature gradually goes up until such point where the temperature is high enough that you get thermal dissociation of hydrogen peroxide to again form a branching of OH, which then leads to the thermal runaway process with hydrogen oxygen to the establishment of a high temperature flame. So it's kind of in this sequence of events kinetically that things occur. So before I describe the statistics, I want to give you a sense of how this problem looks like in a movie. Let's see if I can play it. Well, I don't see. Let me stop sharing and try to play a movie that way. Hang on a second. Okay, it's not letting me do that. Well, we'll come back to the movie. Sorry. Won't let me even do anything.
It looks like you're still sharing on this end.
Yeah, hang on. Let me get rid of the mouse. Okay. Maybe I have to get rid of the pointer. Okay, now, oh, here it is. You have to get rid of the pointer. Okay, I didn't know that. So what I'm going to show you in this rendering is on the left is the evolution of keto hydroperoxide followed by the evolution of temperature. So we're going to denote low temperature ignition by a threshold in keto hydroperoxide of the order of 1e minus 4 mass fraction. And it can also represent a threshold for hydrogen peroxide of about 3.5 e minus 3, which will be shown on the right side on a center plane. And then sequentially, after the first ignition of keto hydroperoxide, which occurs on fuel lean sides, as was shown in the minimum preferred mixture fraction, that plot in the homogeneous case I showed you, then it propagates, that heat propagates into fuel-rich mixtures. And then as the temperature increases to 1150 Kelvin or above, we use that threshold to denote high temperature ignition, which you'll then see in these red platelet-like structures that are the high temperature ignition kernels, which then consume all of the fuel before it establishes a high temperature flame, premixed flame. So here we go. You'll see the first keto hydroperoxide occurring on the outside of the jet. Then you'll see the keto hydroperoxide propagating inward into the shear layer structures. And then about now, you will see the first high temperature ignition occurring on the fuel-rich center core of the jet. These high temperature ignition kernels will then propagate outwards until they reach the stoichiometric, from the rich side back to the stoichiometric mixture fraction surface, and then propagate through some kind of triple flame or edge flame propagation up to the liftoff point, at which point you then have a quasi-stationary diesel jet. I don't know if you saw that, but that's kind of the sequence of the dynamics of events. So what is the upshot of all this for a turbulent autoignition case? It can kind of be summarized here based on this plot of the ignition delay time versus mixture fraction. Same plot I showed you for the homogeneous reaction system, but now I've superimposed on top of that the turbulent auto fluid parcels that have ignited with under turbulent autoignition. The bluish colored isocontours represent fluid parcels that have undergone low temperature autoignition, 50%, and the dashed lines represent the fraction of those parcels that have undergone low temperature ignition. Whereas the red isocontours represent those fluid parcels that have undergone high temperature ignition. I've also overlaid on top of that the original 0D reactor ignition delay curves, red dash denoting the low temperature, black solid is the high temperature 0D ignition. So there are a couple features to note. First, we find that even in the turbulent case, the first ignition that happens occurs at the preferred mixture fraction of about 0.05, as predicted from homogeneous ignition delay. But the first ignition happens later than homogeneous ignition delay because of the high turbulent mixing rates. It dissipates some of the species, the reactive species and enthalpy, and so you end up having a little bit longer ignition delay time. But then once the first kernels ignite under lean conditions, they propagate out into richer mixtures, as you can see in this with the blue arrow. And this is due to both those kernels that have successfully ignite propagate as laminar cool flames into rich mixtures. And at the same time, turbulent transport of those mixtures that underwent very high mixing rates and failed to ignite under lean conditions, that material is transported by turbulent mixing into very rich mixtures as well. And so turbulent transport's fast compared to laminar cool flame propagation. So it's a combination of those two things. But the most interesting thing that we discovered is that under these rich conditions, you can actually ignite faster than you can under the homogeneous 0D reactor. And that is because of transport phenomena. And so we find high temperature ignition actually occurs at about a mixture fraction of 0.16, which is much higher, 0.16, which is much richer than would be predicted, from the 0D reactor prediction, which would have been about 0.12. So you ignite under high temperature conditions at richer conditions due to the bootstrapping of these cool flames and turbulent mixing that brings intermediate species and enthalpy to help bootstrap the spontaneous ignition occurring under very rich conditions that takes a lot longer. And in doing so, you end up having faster ignition under richer conditions than you would get if you just relied on a reactor prediction. And this plot just kind of, I know it's really busy, but it just kind of shows you the turbulent mixing effect statistically. And so if you look at temperature in the first column, and let's just pick one other species like keto hydroperoxide in the third column, what I'm showing you is a time progression. And we've conditioned the data both on mixture fraction as well as on the CDF, the cumulative distribution function of the turbulent mixing, as denoted by the dissipation rate. So high mixing is denoted in green, whereas very low mixing is denoted in black. So CDF of black of the scalar dissipation rate A is like 20% of the peak scalar dissipation rate. And so what you see as we advance in time is the temperature in the first column really does not like to see high mixing rates. It likes to develop under very sheltered conditions. And so the green line, which is the highest mixing rate, exceeding 90% of the max, simply doesn't ignite until much later, whereas the lowest sheltered kernels ignite first. But the interesting thing to note is that for mixture fractions that are quite rich, in excess of about 0.15, you see that the reverse holds under very rich conditions that need high mixing rates in order to bring enthalpy and keto hydroperoxide and formaldehyde transported to the rich side to help bootstrap ignition on the rich side. So it's quite the opposite on the rich side. And you can see that both in temperature, for example, as well as in the ketohydroperoxide, under very rich, under very lean conditions that would be difficult to spontaneously ignite on their own. So on top of this, we then moved to the spatially evolving configuration to look at the influence of multi-injections, with an eye of trying to improve flamelet modeling. And so this is work done with Martin Reith, my postdoc, in collaboration with Mark Day at Lawrence Berkeley, Christian Hase at TU Darmstadt, and Tin-Feng Lewin, a student at University of Connecticut. This problem is motivated by spray A, an experimental spray jet in a high pressure vessel to mimic multi-injection diesel experiments. The experiments were conducted by Scott Skeen, Lyle Pickett, and the most interesting parameter they varied was the ambient temperature of 900 Kelvin, and then they also ran it at lower temperature of 750 Kelvin. With experiments at these kinds of 60 bar pressures, they're limited to what kind of diagnostics they can apply. And so in this case, they used Schlieren imaging and planar laser-induced fluorescence of formaldehyde, shown on the right column, as a function of crank angle degree. And so some experimental observations are that they see that the second injection, well, first they see ignition occurring on the head. It's denoted by these red arcs in time, where you see some softening of the Schlieren image. Those denote cool flame ignition. And then what they see is the second injection, which occurs here, enters the slipstream of the first injection, which shortens the ignition delay time for the second injection, leads to a faster penetration for the second injection. And we also see combustion recession after the first injection, which leads to a shorter liftoff distance for the second injection. What they observed at 750 Kelvin, on the other hand, is that they didn't even see first injection ignite before the second injection started. And they found that the first injection, they could see some evidence from formaldehyde imaging of cool flame products that may help bootstrap and successfully ignite the second injection. And so there's a role of cool flame perhaps in the second injection that's initiated before high temperature ignition starts in the first injection at these lower ambient temperatures. But that's kind of the extent of the information they can get from limited diagnostics. So we thought we could help augment that understanding by performing DNS using this adaptive mesh refinement code PELI-LM. And we tried to mimic the experimental conditions as best we could with ambient temperatures of 900 Kelvin, 750 Kelvin as in the experiment, reduced oxygen, and at 60 atmospheres. We downscaled the ECN spray A. We kept the Domkohler number constant. The Domkohler number is the ratio of the large scale integral time scale compared to the flame time. And the jet Reynolds number here was 19,000, very low Domkohler number of the jet. So very intense turbulence conditions. We downscaled the velocity, the diameter of the jet by a factor of 9, and we also correspondingly scaled back the velocity by a factor of 9. And we kept the same injection schedule as in the experiment, which was a half a millisecond pilot, half a millisecond dwell, and that was followed by a half a millisecond injection of the main diesel jet. Because we were at 60 bar, we had to resolve even finer, down to 1.25 microns to capture the structure of the rich premixed cool flames. And we ended up using a 35 species n-dodecane mechanism developed by Yao et al. And that was used in the previous calculation by Borghese that I just described. PELI-LM is this low Mach AMR code using a spectral deferred correction method for the coupling between the flow and the chemistry. I will just point out that the mechanism we ended up using was built on a USC semi-detailed mechanism for the high temperature chemistry, and then appended to that was were some semi-global reactions for low temperature chemistry, lumped modeled by Pincus and Peters, that were merged to the high temperature chemistry and then tuned and optimized against the Lawrence Livermore low temperature chemistry, detailed chemistry, and against some of the spray A experimental data to tune the NTC ignition behavior. So once we had a compact 54 species skeletal model, we then asked Timfane to reduce that and remove the stiffness such that we could transport 35 species. This just shows some plots of the verification of the ignition delay of the parent detailed model compared with the skeletal model, as well as the flame speed propagation. The propagation speeds as a function of the equivalence ratio at a couple of different pressures. So with this problem, we also went back to the reference 0G reactor calculation again. I apologize, I flipped the axes on you. The mixture fraction is now the y-axis, and time is the x-axis. But you can see in temperature, hydrogen peroxide and OH. Peroxide is a marker of the low temperature ignition, whereas OH demarcates the high temperature combustion. We see that there's two stages of ignition, as we saw earlier, and that for these conditions, low temperature ignition occurs at a preferred mixture fraction around 0.05, whereas high temperature ignition occurs close to stoichiometric. One thing we did with this 0G reactor, which was quite interesting, is that we doped it. We added a little bit of products of combustion to the oxidizer stream, which now consists of an equilibrated lean mixture of mixture fraction of 0.01. Even adding just a tiny bit of product gases to the oxidizer stream vastly changes the ignition picture. What you find is low temperature ignition, as demarcated by H2O2, now shifts to very rich mixtures, 0.15. Before I said the minimum ignition preferred mixture fraction was 0.05. So it's gone a factor of 3 in richness, and it also has decreased the ignition delay time by almost a factor of 2. So at an additive, not an additive, but in training hot products can greatly change where ignition occurs in composition space, and also reduce ignition delay. So I'll show you results first for the 900 Kelvin case. And what you're going to see in this movie is the mixture fraction of the first injection, the pilot, on the left frame, followed by the mixture fraction of the second main injection. And then you'll see temperature in the third frame, the low temperature marker, H2O2, in the fourth frame, and the hydroxyl radical in the fifth frame, demarcating the high temperature combustion. So initially the pilot is injected. Whoops. And you see as the pilot is injected and you have high temperature ignition occurring as you see in the third frame from the temperature. And then we see in the rich side of the flame this generation of ketohydroperoxide, hydrogen peroxide, and formaldehyde. And then you start to see high temperature flame appearing with OH radical along the periphery of this jet. If I play the movie a little further, then we have the main injection coming in, and it's injecting into hot products of combustion left over from the pilot. And so it mixes and entrains hot pilot products that help bootstrap the second main ignition. And we also see here that recession of the second injection. And if we compare then, the ignition delay of the DNS compared with the experiment, we see the first pilot ignites at 0.36 milliseconds. So that's the first occurrence of OH. And in the experiment, we get very good agreement, same rough time, 0.3 to 0.4 milliseconds. The second injection ignites 0.12, 0.17 milliseconds shorter because of the presence of the vitiated gases from the pilot. And that's very good agreement with what's observed experimentally as well. Now, if we go to the 750 Kelvin ambient temperature, this run is still going on and hasn't completed. We see a very different picture. First, we see the injection of the pilot mixture fraction, followed by the injection of the main. But at this time, 1.2 milliseconds, you can see that the pilot injection has not undergone high temperature ignition. The temperatures up here have barely gotten above 750 Kelvin. On the other hand, what you see is the formation of low temperature ignition intermediates like keto hydroperoxide, formaldehyde, and H2O2 into which the main jet is injecting. And so contrary to the 900 Kelvin case, the second injection here is seeing intermediate cool flame products, not high temperature products such as water and OH. We're seeing things like formaldehyde and keto hydroperoxide from the second injection. And so we can then apply a chemical explosive mode analysis, which will allow us to determine the mode of combustion. And this is an eigenanalysis of the Jacobian of the local chemical source term in the governing equations, where y is the vector, solution vector of the various species, temperature, and scalars. And there are source terms that include reaction rates, as well as all of the non-reaction terms, such as diffusion. And so the eigenvalue lambda E that has positive real part is associated with the chemical explosive mode, and is used to delineate any kind of reaction front where the zero crossing to negative values of that eigenvalue occur. And if we project the governing equation onto the left eigenvector B sub E, then we can distinguish between reaction or diffusion dominated regions through this combustion mode indicator that Tin Fang is calling alpha, which is the ratio of the diffusion to reaction terms. And so when the alpha parameter is large and greater than 1, you have diffusion assisted flame propagation. And when you have alpha is less than 1, you have chemical reactions dominating over diffusion. And so you have autoignition. And then when alpha is less than -1, you have diffusion dominates and propensity to quench. And so this becomes a very useful diagnostic for us to determine in different regions of this jet what kind of combustion mode is happening to inform modeling. So if we look at the 900K results, which I showed in the movie, you can see temperature, keto hydroperoxide, the chemical explosive mode. So you can see where temperature is high, you have a crossing between highly explosive modes denoted in red and exhausted modes, negative eigenvalues in blue. So those regions coincide with where product gases exist, where you see the blue spots. Otherwise, the rest of this is highly reactive in the shear layers and in the bulk of this jet. Now, if we applied the augmented SEMA analysis, we identified that the periphery of the jet is dominated by autoignition, whereas the interior of the jet is primarily dominated by flame propagation assisted by reaction or autoignition, in addition to the dark blue regions, which indicate local quenching or slowed down reaction due to diffusional losses. If we then condition the statistics, we find that the keto hydroperoxide, conditional on the mixture fraction, sum of the pilot and main, we see it's present on the rich side, where Z stoichiometric is here. And this is consistent with what we found in the temporal jet by Borghese and also earlier work by Rainer-Gams. We then further conditioned the statistics of the first low temperature injection on the conditional volume integral, conditional volume integral of the keto hydroperoxide conditioned on the volume integral of the cells that correspond to these different modes of combustion: diffusion, ignition, flame propagation. And we condition it on the sum of the mixture fractions. And so for under rich conditions, the upshot is that keto hydroperoxide, low temperature soup, correlates to the combustion mode that's dominated by diffusion or supported by diffusion, that is flame propagation, cool flame propagation into a reactive soup. And so any model, combustion model, that subfilter combustion model would need to be able to account for this. The second injection shows a very similar picture. If you look at the second injection for 900 Kelvin, you see the blue and the red denoting the flame propagation aspects, either helping it or hurting it. And then around the outer edge, you see autoignition being the main mode. We can further get modeling statistics such as the explosive mode conditioned on the mixture fraction sum and the progress variable. And these would be statistics that would be useful for a flamelet generated manifold model or for a flamelet progress variable type of model. And the interesting signature here of multi-stage ignition is the SEMA switches from red to blue, explosive to exhausted for low temperature ignition, and it does it once again for high temperature ignition. We can see then that the KEAT in other low temperature radicals like formaldehyde, if you plot them versus the mixture fraction and progress variable, it exists in this region where you see very rich conditions and low values of progress variable that coincide with the SEMA analysis for low temperature ignition. Likewise, if you plot OH versus the mixture fraction and progress variable, it lives out in the space close to stoichiometric and under very high values of progress variable, which coincide with this chemical explosive mode, the second crossing of the chemical explosive mode indicating the high temperature ignition. And so I think the DNS data can provide a wealth of these kinds of joint PDFs of mixture fraction progress variable or even age variable for the purpose of subgrid scale modeling. Okay, and so we performed DNS of the simplified spray A experiment. We found accelerated ignition for main injection that was consistent with the experiments. We found that the DNS provided a wealth of data for improving both the understanding as well as for model development. The chemical explosive mode analysis is a useful tool to understand which combustion modes occur in which part of this jet. And we found that strong mixing inhibits ignition of the first jet, but it promotes ignition of the second jet. I will just briefly touch upon the reheat combustion problem. This is a problem that Aditya Kanduri, Andrea Gruber, Mirko Bothian, and I worked on a year or two ago, and involves sequential staged combustor that Ansaldo Energia is building. It used to be Alstom, the GT36. And what's shown here are isosurface plots of the vorticity magnitude colored by temperature in the mixing duct that follows the first stage combustor. And then there's a sudden expansion into the second stage combustor, which is autoignition dominated. And so you can see the temperature of the wall is at 750 Kelvin, and the temperature in the combustor as colored by these yellow entropy is well over 1500 Kelvin due to the autoignition products. The heat release plot is plotted, isosurface is plotted here as this conical structure due to autoignition that exists. So as I mentioned already, this is a staged gas turbine combustion system improved by Ansaldo Energia. And the first stage is premixed combustion based on flame propagation and anchored on vortex breakdown and mixing. Second stage is based on autoignition. This is the DNS configuration here with an inlet temperature of 1100 Kelvin, pressures 20 atmospheres. We scaled it back down to 1 atmosphere first and kept the other parameters about the same. So our objective here was to understand how the flame stabilizes, what are the modes of combustion, and then quantify the role of autoignition. Here we took the S3D code and we extended it to be multi-block. So it's like putting together Lego blocks. Here there are 4 blocks to comprise the mixing duct, which had a length corresponding to the ignition delay length of that vitiated hydrogen air mixture that was coming in. And then we have the combustor out here. Chemical mechanism was hydrogen air with 9 species using Lee et al. The inflow composition was vitiated hot combustion products from the first stage mixed with hydrogen and oxygen to an equivalence ratio of 0.35. The turbulent flow had a bulk velocity of 200 meters a second. 10% of that was the RMS velocity. It's highly preheated inlet at 1100 Kelvin, and the wall temperature was cooled at 750 K. We obtained the inflow profile for the turbulence from running a separate channel flow, fully developed turbulent channel flow, and then sampling the feed data at the inlet plane. The bulk Reynolds number was 13,000, whereas the viscous boundary layer Reynolds number is 378. Here we find two design state, in the DNS, we observed two different configurations. One was the design state, which is desirable. We wanted most of the combustion to occur in the chamber, combustion chamber, and due to autoignition. But occasionally we would see intermittent autoignition state where ignition kernels would form in the mixing tube, which is undesirable and could lead to thermoacoustic problems. So let me first talk about the design combustion state. Here, we've taken a slice of the data along the center plane, and you can see from the heat release temperature and HO2 mass fractions, autoignition occurring along the center line, whereas just behind the sudden expansion, you have a region of flow recirculation of hot product gases that anchors these thin premix flames that propagate near the corner from the boundary layer reactants that are too cold to ignite or burn in the duct, but when they encounter these hot products, they ignite and anchor this autoignition in the corners of this sudden expansion. We then looked at OH budget analysis to tell us what mode of combustion was happening where. And if you look at the OH radical species continuity equation, there are terms associated with advection, diffusion, and reaction. If we take a cut along the center line of the combustor, point A, we see that, and that is shown here in this bottom left plot, we see that there's a nice balance between advection, shown in blue, counterbalanced by reaction in red, where transport diffusion is negligible. And so this is a signature of autoignition happening along the center plane. If we then take a second cut near the corner, we find just the opposite. We find a nice balance between, in this cut B, between diffusion in green counterbalanced by reaction in red, which is the typical premixed flame structure. And so we anticipate deflagration occurring in these corners. We then ran the chemical explosive mode analysis, which is an independent check of the different modes of combustion. As I talked about before, this alpha parameter, which is the ratio of the diffusion to reaction source term, projected on the projection of these source terms onto the left eigenvector. And again, red denotes the flame propagation assisted by autoignition, blue represents quenching, and green represents autoignition. So we see very clearly, consistent with the budget analysis, flame propagation near the corners, whereas the bulk of the combustion happening in this cone-like structure is autoignition. If we weight the percentage of fuel consumption conditioned on alpha, we find that over 80% of the fuel is consumed through autoignition, with much less due to flame propagation for the conditions I am considering here. Now that percentage shifts as you go up in pressure and vary the conditions, but I won't talk about that today. The other intermittent autoignition state that we observe is shown here, and this was not very welcome. We saw early autoignition happening in the mixing tube, and then we see the ignition kernel advex downstream into the combustor, and then this sporadically occurs over and over again. And so we were wondering, and it's very clear from the HO2 radical, which shows this ignition in both the combustor as well as in the mixing tube. The cause of this is due to the autoignition, predominant autoignition in the combustor, which leads to acoustic waves that emanate from these ignition in the combustion chamber that propagate outwards as well as upstream. The upstream is concerning because these waves form constructive interference patterns with the walls, both the longitudinal and lateral waves, And this leads to isentropic compression, as you can see from this contour plot of the instantaneous dilatation field. And so that's a negative dilatation. And that isentropic compression also leads to an increase in the temperature by about 20 to 30 degrees Kelvin. And hydrogen being so reactive, that tiny bit of temperature increase can drop the ignition delay time by as much as 30% and cause the ignition phenomenon that we saw in the mixing tube. And so here we've performed DNS, a reheat burner at scaled conditions. We're now doing similar runs at much higher pressures at 10, 20 bar. And we found two different states, a design state and an intermittent autoignition state. And we've quantified the contribution of different modes towards heat release and fuel consumption based on SEMA. And so now I'd like to, with my remaining time, talk a little bit about the computer science issues. So to make these runs on Summit.
We do need to wrap up, Jackie.
Okay.
We're 10 minutes past the hour.
Oh, how about a minute?
Sure, minute is great.
All right, so we are now using the Legion programming model, which is a data-centric programming system for GPUs, and it automates a lot of the aspects for getting high performance, such as extracting task and data level parallelism. It automates how you schedule tasks and data movement on the machine, so it's not hand-baked in at low levels of your code through MPI. And it separates the specification of the data and the tasks from the mapper onto a machine so that you can easily achieve performance portability to other machines. And so we have gotten 4x improvement over an MPI code with Legion at low node counts and as much as 7x improvement at higher node counts due to Legion's ability to hide latencies across the interconnect. This was done on Titan, and we get another 34-fold speed up on Summit. And then I want to just say that because it can hide latencies and interleave communication computation for you dynamically, we're able to include in situ analytics almost for free. And so including that expensive eigensolution with SEMA on the fly, without SEMA, on the left here, we see a time of 6.79. And with SEMA, it was about half a millisecond longer using just MPI, but on using Legion, you get it almost for free. And so we saw a 98% reduction in the cost of in situ analytics using Legion code for some of these complicated eigensolution problems. And so very last point I want to make is where we're headed is trying to do surrogate DNS using in situ adaptive principal component transport to help us reduce this high dimensional composition space and potentially reduce the savings in costs by 2 orders of magnitude. And so I will be happy to talk to you individually about that work. So it's basically PCA transport of a few principal components as opposed to thousands of species. And we will also use anomaly detection using joint statistical moments, higher moments, as a trigger for adapting PC transport subspace on the fly in the DNS, since we see a lot of very transient intermittent phenomena that a static representation of the principal components can't capture. I'll stop here.
Thank you very much for a very interesting talk. We are over time, but if there's questions, please unmute yourselves and ask, or you can send it to me in the chat. There was one.
Hi, Jackie, it's Ahmed. Hi, how are you? So it's a very interesting talk, and I have a longer question that I will keep to our private conversation an hour or so. But I just wanted to ask you whether in any of the ignition studies, you also looked at potentially the impact of the local strain race on delaying the ignition beside the chemistry effect.
Yes, we did. We looked at, I didn't plot those, present those plots today, but we did. We looked at the scalar dissipation rate as well as the cross-scalar dissipation rate when you have multiple injections. And the upshot is ignition kernels really do not like strain rate when they're forming early on. But once they're developed to a point, then they like having high strain rate because it helps the mixing and development of further development of the kernels. But early on, they want to form in very sheltered regions, and that's why in one of the statistics I showed you, a lot of the on the rich side where the jet's very strong and you have high strain rate, a lot of that material doesn't successfully ignite, but then gets turbulently transported into very rich mixtures, which brings matter over there, heat and matter, that help the spontaneous ignition bootstrap itself to the point of high temperature ignition.
So there was a question about the future of particle-based methods and how do they fit within this very massive parallel computing resources that we have now.
So is the question related to Lagrangian, like a PIC code, particle and cell code?
Or just Lagrangian methods for solving the fluid dynamics?
I'm only familiar with using particles for solving multi-physics like sprays or soot.
Okay.
The only other particle method, I know Ahmed's very good at, vortex, Lagrangian vortex methods.
Okay.
The only other particle method that we're using is more in the mesoscale, where we're using Monte Carlo simulations. But that's a different regime, right? When we're looking at non-equilibrium, thermal or chemical non-equilibrium, we're using particle-based methods there. But we're not using Lagrangian vortex methods, and Ahmed's the expert on that.
Okay. So there was one question about the details of the finite difference schemes that you used. I think what order methods were those?
Yeah, so the finite difference method is 8th order centered in space and 10th order filter. And then in time, it's a 4th order method in explicit Runge-Kutta method by Carpenter and Kennedy.
Okay, great. Any other questions?
Well, I wanted to also say that the Peli codes are open source, and there's a GitHub repo. So if anyone wants to try it out, welcome to take a look at the code.
And so you, in one of your calculations, you said those were still running, one of them.
Yes.
So what kind of run times are we talking about generally?
So we get a lot of runs that take 50 million CPU hours on the supercomputing centers running on 1,000 nodes on Summit, which would be 6,000 GPUs, or on a significant fraction of the machines at NERSC on Cori. Yeah, they're very expensive runs. And so our hope is to generate and archive these data sets for the greater community to use either for physics-based model development or for machine learning AI. And so we're trying to annotate the data and make thumbprints and so on, so that people can easily access the data if they wish to.
I have a question.
Yes.
Can you please where is this GTOB repository located? And if you can repeat the schemes you use and the orders of those schemes again, that would be nice.
Oh yeah, 8th order in space, 10th order in time. I'm sorry, 8th order in space, 10th order filter, 4th order explicit Runge-Kutta. It's a 6-stage 4th order method by Mark Carpenter and Chris Kennedy. I think they have papers on both of those, the space and time differencing. We started out using a 6th order Pette scheme, but we got rid of it because it required a Thomas solve, which made it difficult to scale up on these distributed parallel machines. We moved back to just using a higher order centered finite difference method with just.
And at, I think you said 2 billion CPU cycles. How many days is that anyway?
I didn't say 2 billion cycles. I said it takes about 60 million CPU hours.
Oh, 60 million. How many days is that anyway?
It's a couple of weeks running on 1,000 or 2,000 nodes on Summit. You don't get all that time at once, so you could probably finish a run in a month or 2 months, you know, sporadically when you're allowed to get in the queue.
Thanks.
Yeah. Any other questions? Okay. I'd like to thank our speaker once more for a very interesting talk. Thank you very much. And that concludes, oh yeah, okay, that question was asked, yes. That concludes our talk today. Thank you very much for attending and for a very nice presentation.
You're welcome. And sorry for going over.
No, it's okay, it's okay. Thank you.